So hi everyone, welcome to the ASC seminar. And today we're happy to have Jasper Lee, who's just finishing up his PhD at Brown University, and he's been working on problems in algorithms and complexity and statistics. And today he's going to tell us about some exciting results on Sub-Gaussian mean estimations. And without further ado, I'll let you take it away. So go ahead, Jasper.
Great. Thanks for the introduction, and thanks for inviting me here. I'm Jasper, and today I want to talk to you about what is perhaps one of the simplest questions in statistics. How do you estimate the mean of a real-valued distribution? So let me just start by phrasing very concretely exactly what I mean by this problem, exactly what formulation we're considering here. So in our setting, we assume that there's some unknown distribution D that is distributed over the real numbers. And what we want to do is to estimate the mean of the distribution, or find an estimator to estimate the mean of the distribution from, let's say, n IID samples from the distribution, such that the additive error we want to be less than or equal to, let's say, epsilon, this parameter epsilon, and we want to fail with probability at most little delta. So this is a very standard PAC kind of, epsilon delta kind of regime, a high probability regime. And the question here is, how do we, can we find an estimator, some mu hat, such that we minimize the sample complexity, the number of samples we need in order to achieve this epsilon delta guarantee? Okay, so now you might be wondering, okay, this sounds like a extremely basic problem. Is there a problem to be solved to begin with? So let me use a couple of slides to motivate that there is actually a problem to be solved, and there's something interesting going on. So for the structure of the talk, I'm going to motivate the problem a little bit before I state the main result, and our actually pretty simple algorithm. And I want to give you some intuitions about how the estimator works before diving into the more technical part, which is about the analysis, which is interesting, but also a little bit more technical. Right? So diving in, the first thing you might be wondering is, okay, so we're doing mean estimation. Surely we just take the sample mean or the empirical mean, namely you just take a bunch of samples, take the average, and use that as the estimate. So the first thing I really want to say is that the sample mean is known to be not optimal, even in one dimension. That is more formally captured by Catoni, who started this whole line of work in his 2012 paper, formalizing that it's actually a pretty bad estimator. So, of course, the sample mean, there are good properties about it. So, for example, the sample mean is pretty good in various Gaussian settings. It's a very good streaming algorithm, for example. And it's somewhat robust to correlations as well in your sample. So it doesn't really need the IID assumption. On the other hand, if we actually do go back to the basic question of IID samples, the sample mean is known to be really bad for distributions with heavy tails, essentially. Anything with a tail that is heavier, substantially heavier than the Gaussian. Now, you might be wondering, if you not really in this line of work, you might be wondering, oh, what about all the concentration guarantees that we learn about in, let's say our first class in randomized algorithms? What about them? So in general, what happens is that if you look at different concentration inequalities, you need to apply different kinds of assumptions, and you get different kinds of sample complexity bounds. So let me give you a couple of examples. If you make, for example, an assumption that the distribution has a Sub-Gaussian tail, then you can solve, apply a corresponding tail bound and get this sample complexity, where sigma squared is the underlying variance of the distribution. And again, epsilon is the additive error accuracy we want to get to, and delta is the failure probability. On the other hand, if you want to generalize this a little bit, apply a weaker assumption, well, technically not comparable, but it feels like a weaker assumption. If we apply Bernstein's inequality instead, what we assume is that the distribution is supported within some close bounded interval, let's say constant width. In which case you solve for the sample complexity and you get something slightly different, with the difference being this 1 over epsilon term. And the thing I want to point out here is that this term might dominate the first term in the case where the variance is extremely tiny in the underlying distribution. So in general, what happens is that as you apply different kinds of tail bounds, you need to make different kinds of assumptions, and then you solve for different kinds of sample complexity. So if you apply a smell test to this whole thing, it just smells like that the sample mean isn't actually optimal. And indeed, what Catoni showed is that it's actually exponentially bad. In fact, the dependence on the failure probability of the convergence of the sample mean is exponentially worse than this, common logarithm that we're used to seeing. And the thing I want to just point out is that this convergence right here, never mind really the concrete expression, but this is what you get if you only apply Chebyshev's inequality. So all the niceness we get from tail bounds, that the exponential convergence, the sample mean doesn't actually enjoy that in general, unless you make additional assumptions. So hopefully I've convinced you that there's something to be done here. Right. So, okay, so I hopefully motivated that the sample mean doesn't actually work in general. So what is the goal? Like what are we, what should be the objective? What are we, what's the sample complexity we want for a good estimator? And for that, we want to look at the Gaussian case, just because Gaussians tend to be edge cases of a lot of problems. And in the Gaussian case, the problem is actually pretty simple to calculate, is very well understood. As I mentioned before, the sample mean is actually optimal in the case of Gaussians. In particular, it has this sample complexity, this Sub-Gaussian sample complexity you saw on the previous slide, with this multiplicative constant of 2, with a little bit of little or one term that I'm not going to discuss. So the point being that we know the constant 2 times this expression, that will be an upper bound to the sample complexity. And it's also actually not hard to show that there's a lower bound matching, essentially, up to this 1 plus little or 1 multiplicative factor. So this same constant of 2 times this expression is actually tight for the Gaussian case, which motivates the question of, can we actually find a mean estimator that not only works for Gaussians, but we want the same sample complexity for all distributions with finite variance. So we want to vastly generalize this Sub-Gaussian guarantee with this constant of 2 to the entire class of distributions with finite variance. And of course, as I'm going to explain for the rest of the talk, the answer is yes, we can actually find such an estimator, and it has a bunch of nice properties as well. At this point, I want to contrast with what is known, what's previous work prior to what we've done. So as I mentioned, Catoni basically started this whole line of work where he was focusing on getting this right sample complexity, but making additional assumptions. So the assumption he made is that where in the case where you actually know what the variance is, so not only is the variance finite, but you have knowledge of pretty much exactly what it is. So in that case, he wrote down an estimator with this sample complexity. It's also been generalized in other works and also in Catoni's work, actually, where instead of assuming a finite variance, if you only assume a finite fourth moment, and in particular, this fourth moment is bounded by some parameter, then essentially what happens is that in that kind of regime, you can use that to estimate the variance and then plug it back into kind of Catoni's framework. So in which case, if you assume a finite fourth moment assumption, you can also get this sample complexity. And also the other on the if you don't care about constants, if you don't care about this concept of 2, I just want to mention that it's all been known for a few decades, actually, how we can get this sample complexity in a bigger sense. And that's via the very standard medium means estimator. Any questions thus far? Yeah. Great. So, okay. Actually, there's one more thing I want to mention.
To be clear, this is all 1D so far, right?
This is all 1D, and I'll only be focusing on 1D for this talk. Yeah. Another thing I want to mention is, okay, so this finite variance assumption. So you might be wondering, can we? Okay, some other work have been doing finite fourth moment assumptions. So what happens if you try to strengthen the moment assumption and weaken it? What happens? So the thing to note is that if we assume any finite moment bigger than the second moment, it doesn't change the nature of the problem, because as I mentioned a couple of slides earlier, the lower bound is from Gaussians, and Gaussians have all finite moments. Like all the finite moments are bounded and well defined. So making any assumption bigger than the second moment doesn't help the problem. Now, what if you don't make a finite second moment assumption and relax that, maybe only assume that it has a finite 1.5th moment? in which case it turns out that the sample complexity changes very drastically. In particular, this dependence on epsilon currently is epsilon squared. If it's only 1.5, then it will be epsilon to the, oh, actually, I forget. It's something bigger than 2 anyway. So point being that this finite variance assumption is exactly the right threshold to get this kind of Sub-Gaussian sample complexity. And this is, which is why we were focusing, or this work focusing on exactly this class of distributions, which is kind of the right kind of cutoff for movement assumptions. Okay, so with that, having described the problem, let me now actually state the result formally. So the result, as I mentioned, is for the entire class of finite variance distributions. And if you want to have additive error epsilon failing with probability at most delta, our estimator has this right sample complexity with this tight constant of 2. And in fact, it even computes in linear time. So the computational aspect, I won't be focusing on in this talk because that's not as interesting as the statistical aspect. Now, one thing to notice in this theorem statement is that the sample complexity, in fact, depends on something we don't know, namely the variance of the underlying distribution. So I, kind of emphatically said that, we don't assume any knowledge of the variance, and we don't assume any movement assumption such that we can estimate the variance. So this kind of theorem statement isn't particularly useful because it's currently phrased as, given an epsilon, given a delta, can you minimize n? But then n depends on something that's unknown. So we can kind of reparameterize the entire theorem in the following form. So instead, what we want to do, a more useful form of the theorem is to say, fixing n samples, and then we fix a failure probability delta. What is the smallest additive error we can get? And this is pretty much just a rephrasing of the previous theorem that says that our estimator satisfies some additive error, some convergence guarantee that is tight to within the 1 plus little or 1 term. It doesn't really matter for the purposes of this talk exactly what this expression is. But the only thing you need to know is that this is tight to 1 plus little or 1 term right here. So this is just a rephrasing of the theorem, and it's a more useful form of the theorem that you can actually apply in practice. So without further ado, let me actually state the estimator.
So Jasper,
yeah,
just one
please.
question. So in the first form of your theorem, so for higher dimensions, like, does this 2 get replaced? Is only the 2 that gets replaced by something else, or what is the?
Yeah, so in high dimensions, the question is somewhat more complicated. In particular, so we understand the high dimensional case in the big O sense, and the issue is that basically, let me phrase it in this form, in the additive error form. What happens is that there are actually going to be 2 error terms, like big O of 2 error terms that kind of dominate each other in different parameter regimes. One depending on this high probability regime, and one depending on the trace of the covariance. So like the sum of variances essentially. And yeah, the problem becomes a lot more complicated, and it isn't even clear what it means to get a tight constant in that sense, because that would require understanding exactly which regimes, which term dominates each other.
Oh, I see.
Yeah, so the high dimensional question is a lot more complicated than this one dimensional question that we studied.
I see. And the 2 plus little o of 1 that appeared over there, like here, where is
this 2?
Is this 2 over here?
Yeah.
Okay.
Yeah, and the little 1, yeah, I just pulled it out, but yeah.
Okay.
Yeah.
Thank
but
you.
yeah, so this is not very important. It's just reparameterizing the equations essentially. It's easy to derive. So, but yes, without further ado, let me actually show you the estimator. And it fits on one slide. It's a very clean, very simple estimator. So the first thing, well, we want input. So again, n samples, and we want to specify what probability we're willing to fail with. So the first thing we're going to do is to just compute the median means estimate from the samples, which, as I mentioned, this is already a big O type, so it's a very good estimator already. It's just not tight in the even in the constant. So already a pretty good estimator. So what we now want to do is to turn this very good estimate, already pretty good estimate, into something that's optimally good via this transformation, by these 2 steps. There are 2 equations here. I will explain in the next couple of slides exactly what they mean. But let me just say that operationally, what we do is we solve for this alpha parameter in this first equation. The thing I want to note right now is that this equation, the left-hand side, is a piecewise increasing linear function in alpha. So that there is some structure that allows us to solve for this alpha somewhat efficiently, in fact, in linear time. And then what we do is we just plug in alpha here and compute the sum. And that gives me the second estimate, the final estimate. So again, this is kind of like a bootstrapping step, a pretty good estimate. Solve for alpha, plug it in, that gives me the final estimate. Yeah, so this is a very simple estimator. You can, put it in a first year programming class. Students hopefully will be able to implement this. But the question now is, okay, so what exactly do these two slightly messy looking equations mean? So let me offer you a more intuitive explanation of what this estimator is actually doing beyond, slapping two equations on the slides. So now what I want to do is offer you an interpretation of the estimator, and I want to briefly justify at least parts of the construction before talking about the analysis. Okay, so let me put those two equations back on the slide again. So again, we compute the median means estimate, solve for alpha in the first equation, and then plug it into the second equation to get our final estimate. So in order to really interpret what's going on, let's try to simplify this whole mess a little bit. The first thing I want to say is that it's not hard to show that our estimator, as a function of the samples and delta, it respects shift and scaling in the samples. Namely, that if you apply some affine transformation to your samples, like some consistent affine transformation, the final estimate is going to respect that affine transformation as well. So what this means is that it suffices to analyze our estimator for mean, zero, and variance one distribution. So instead of the whole class of finite variance distributions, we normalize all the distributions essentially. So why is this useful? The next thing I want to mention is that if you treat these two equations, it's mapping some preliminary estimate into a final estimate, right? So if you treat this procedure as a real-to-real function, this is actually very insensitive to what kappa started out being. It's very Lipschitz, like there's a very small derivative in kappa. And combining with the fact that the median means estimate was already very good to begin with, what this means is that this allows us to pretend, essentially for the purposes of analysis, that the median means estimate is actually the true mean. Like we might as well only analyze it when we plug in the true mean and see that it's going to give me a final estimate that is accurate enough. So what this means is that I can assume kappa equals the true mean, which by the previous assumption means that it's actually equal to 0, which lets me simplify these two equations to a slightly more palatable form. Does that make sense so far? So, okay, so still, I've got these two equations. So using the simplified form, let me now explain exactly what the estimator is doing. So let me first draw your attention to the second equation and ignore this 1 minus bit. If you ignore this 1 minus bit, what I get here is really just a sample mean, right? So what our estimator is doing instead is for each sample, we are going to subtract this red fraction from the sample before computing the sample mean. So we're doing kind of each sample, we are going to assign it a weight that is smaller than 1, between 0 and 1. Okay, and then we're going to compute the sample mean based on this weight. Now the question is, so how much do we truncate from each of the samples? That's governed by the first equation. Turns out the right thing to do is to truncate a total weight of 1/3 of log 1 over delta. This is the bit I'm going to explain why this magic number on the next slide. But point here is that we're going to truncate a total amount of weight in samples that is equal to 1/3 of log 1 over delta. In terms of how we distribute all this weight, we're going to distribute it according to the square distance from the true mean. So if a sample is really far from the true mean, we're going to square its quadratic distance, and it's going to get that proportion of weight from this 1/3 log delta that will be trimmed away. And the min with 1 simply means that we're never going to try to truncate more than the entirety of a sample. So yeah, this is a very operational meaning to what these two equations actually mean. We truncate a 1/3 log 1 over delta many samples, and we spread out the truncation weight according to its square distance from the true mean. And then we compute the sample mean. Now, as I mentioned, what is perhaps the most unnatural thing about the estimator is this like 1/3 log 1 over delta, like magic number right here. So let me try to explain through a simpler example why this is the right number of samples to truncate. So to motivate that, let's look at the very simple case of Bernoulli coins. So we want to estimate the mean of a Bernoulli coin with bias P, and we do that via n coin flips. So the interesting regime in this problem is when the bias of the coin is really, really small, so it's a very rare coin, in which case, so most of the coin flips are going to be tails. So the number of tails doesn't really offer anything interesting about interesting information about the true bias of the coin. So we care about the number of heads, the distribution of the number of heads. That's where the crucial information is coming in. And in a strong limit sense, the number of heads of n flips of a Bernoulli coin is distributed as a Poisson distribution with the parameter that is the product of n and p. So what I've done on the right is to plot two graphs. The blue dash curve is the logarithm of the Poisson, the corresponding Poisson. I've taken the liberty to choose lambda being equal to 100. So a Poisson curve. And the benchmark we're kind of trying to compare ourselves against is the Gaussian, because the whole point of this project is to get Sub-Gaussian concentration. So we're going to compare with the Gaussian PDF with the same mean and variance, also 100. So this is the red solid curve. So how does a 1/3 log 1 over delta fall out of this picture? So it turns out it's really simple. If you look at the delta tail of both of these distributions, by delta tail, I mean to the right of the point, there's delta probability mass. So for these two distributions, there are two delta tail points. This gap is going to be up to approximations. This is going to be a 1/3 log 1 over delta. So what you want to do is basically just shift the Poisson curve to the left, namely you subtract the number of heads you've seen by this 1/3 log 1 over delta number, and then you divide by n, and that would be a good estimate because that matches the two delta tails. Does that kind of make sense? And yeah, so one thing I want to note here is that the 1/3 log delta, like in order to actually derive it, at least through approximations, but really deriving it, that comes from taking a Taylor expansion of the exponent of a Poisson PMF. If you expand that to the 3rd order, so what happens essentially is that if you take the logarithm or just the exponent of the Poisson PMF, the first 2 order terms are going to match the Gaussian, and then there's some 3rd order term that's lingering. Essentially, what this 1/3 log 1 over delta term is doing is correct for this 3rd order kind of skew in the distribution. And in general, I'm happy to talk more about this offline, but in general, our estimator could be interpreted as some notion of 3rd order correction to the sample mean as well. But yeah, that's something that's not in the presentation itself. I'm happy to talk more about it offline. Any questions at this point before we dive into the analysis? I think this is a good point to pause.
Hello?
Hello?
Yeah, just maybe a quick question about the interpretation. Like you're given n samples, and once you're given the samples, everything's deterministic, right? So is there a way to see your algorithm is doing something to this set of points? Like you said, throw away this fraction. Like what thing am I reaching for a deterministic set of points?
Sorry, well, what do you mean by a deterministic interpretation? So yeah, what we're doing is throwing away a bunch of, like fractionally, each sample, we're throwing away some fraction of it and then computing the sample mean. Is that?
Right, so you gave a nice interpretation of why we should do this if your input distribution is coin flips, and so I want to match the 3rd moment of the Gaussian, right?
not the third moment of the Gaussian. It's kind of like a third order correction from the Poisson to the Gaussian. But
Right. My
you
understanding was
asking-
that this is how to interpret it as a way to change the random distributions, right?
right, yeah.
So I'm saying, is there also an interpretation just for these points? Like, once you've given me samples, like, then what are you doing?
So, sorry, let me see what I'm understanding you correctly.
Sorry if this is confusing.
So, I mean, okay, so this slide here, the interpretation, the throwaway number of samples, that itself is a deterministic procedure, right?
Uh-huh.
So I think this kind of answers your question of what it is doing to the samples. What I was talking about on this slide is why we're doing that. And then that inherently needs to come from some probabilistic, the probability needs to be in the picture, right? Because ultimately, this is a statistical problem.
Right.
Does that make sense?
Yeah, thank you.
But yeah, any other questions before I move on to the analysis? Great. Okay, so right. So for the analysis, again, these are the two equations that we somehow need to analyze. That this pretty much captures the estimator. What we want to do is, if you recall, the main theorem is really just deriving tail bounds for our estimator. So a very natural approach is to derive our own very custom kind of Chernoff bound. And by a Chernoff bound, I mean a bound of the following form. Some random variable x, we want to say that the tail probability of it being bigger than some number, this is bounded by the moment generating function divided by some exponential term involving epsilon. So this is the standard Chernoff bound. This is the overarching approach I want to use to analyze this estimator. But we quickly run into two issues. And these two issues are the resolutions are what I want to talk to you about for the rest of the talk. Okay, so the first issue is that this moment generating function, it's going to be really hard to handle because our estimator, despite being a sum, is not a sum of independent things. In fact, all these terms are dependent on each other. They are correlations. To see that, just first, let's try fixing alpha as a constant, in which case each of the terms would be just a function of these xi's. So that would be a sum of independent terms. However, alpha is not a constant, but in fact comes from the first equation, which involves all the samples. So this alpha is kind of introducing dependency between all the summands in the sum. And the nice thing about sums of independent terms is that the moment generating function factors out like very nicely. And here, like if we just try to analyze the moment generating function, we don't have any such factoring, and that becomes really hard to analyze. So this is the first obstacle that we're going to face, that I'm going to tell you about the resolution of. The second obstacle is that, let's say we even get around that issue. Still, the question remains, how exactly do we bound the moment generating function? Now, note that in standard Chernoff, like standard tail bounds in general, we make much stronger assumptions. Like for example, Sub-Gaussian tails or bounded support and so on and so forth. Here we're trying to analyze the moment generating function for all distributions with finite variance, which is a significantly larger space. And somehow we need to get really tight bounds for all of these distributions. So the question is, how do we actually bound the moment generating function? Even ignoring the issue of not having independence between our summands. So these are the two problems I want to talk to you about and offer resolutions to. And I hope or believe or hope that this framework, the resolution to these two questions, gives a nice, somewhat new framework for that might be generalizable to other problems as well. Okay, so to resolve the previous two questions, here's what we're going to do. So that's the outline for the rest of the talk. The first thing we're going to do is to reduce the main theorem to proving Chernoff bounds, not directly on the estimator, but we're going to find proxies of the estimator that will turn out to be sums of independent terms. Okay, so just don't analyze the estimator directly. I'm going to find proxies that gives me independence. And then what happens is that once we try to do the channel finite analysis, it turns out to be some really horrible, like infinite dimensional optimization problem. What we're going to do then is to use convex concave programming duality and linear programming duality to turn that into something finite dimensional and at least sounds somewhat tractable from the original thing. And then for the rest of the analysis that I won't be talking about in the talk, it's just inequality hacking and slashing, not particularly insightful. So these two are the main conceptual messages that I want to bring from the analysis in this talk. Okay. So, okay, again, we've got these two equations. That is my estimator. Solve for alpha in the first equation, plug it in, that gives me the final estimate. So in order to find these nice proxies that we can use to analyze the estimator, the first thing I'm going to do is to rewrite that into a completely different form. If you know what that means, it is called a psi estimator. But in particular, here we have 2 parameters and 2 equations. But let me just state exactly what I'm doing. I claim that this estimator is completely equivalent to solving for the roots of these 2 equations. So these 2 equations depend on the samples, some candidate mu hat and candidate alpha. And we want to solve for mu hat and alpha such that both are equal to 0. And this is not hard to see that these are exactly the same estimator, simply because the first function, this thing, is simply really just the left-hand side subtracting the right-hand side of the second equation. And similarly here, this function, this sum, is really just left-hand side subtracting right-hand side. So naturally, what we would have produced here would be a root to these 2 equations. So, okay, well, this sounds like a silly kind of rewriting. So why are we doing that? The thing I want to point out here is that if we fixed mu hat and we fixed alpha, each of the individual sums are now sums of independent terms. So we're making a little bit of progress towards getting independence. But now we've got 2 of these sums. The question is, how do we only get one that we can prove Chernov bounds about? And the other thing is that now that I've completely rephrased what the estimator means, and again, the estimator is solved for the roots of these 2 equations, it's helpful to try to rephrase exactly what it means for the psi estimator to produce a good estimate, just to put it in the language of these psi estimators. So for that, I have this following lemma that shows the equivalence of just rephrasing the same kind of sentence in different language. So the first condition is very simple, which says that our estimator, given a particular sample set X, it outputs an estimate that is close to the true mean by additive error less than or equal to epsilon. Okay, so that's the success condition, that's the victory condition. Now the question is, can we rephrase that in terms of the psi estimator? And I claim this is equivalent to this statement, the second statement. The second statement says that for every pair of mu hat and alpha, such that mu hat is a bad mean estimate, namely that is too far from the true mean, it must be the case that at least one of these 2 equations are non-zero. Because otherwise, we would have solved for, if both were 0, we would have solved for this pair of mu hat and alpha and returned this mu hat. Yeah, so I'm just rephrasing what it means for the the estimator to return a good mean estimate. It's a condition over all the bad pairs of mean estimate and alpha pair. But this condition is also not very nice looking. In particular, we have a disequality and a disjunction here. So that's not a very smooth kind of mathematical condition. So let me rephrase that just a little bit more. This is also equivalent to the following. Again, quantifying over all pairs of mu hat and alpha such that we have a bad mean estimate, then it must be the case that there exists some 2 parameters, d mu and d alpha, such that the linear combination is bigger than 0. That naturally comes from the fact that one of these have to be non-zero. Okay, so I'm just rephrasing what it means for the estimator to return a good estimate in the language of the psi estimators. And the other thing I want to point out is that this linear combination, if d mu and d alpha are constants, this linear combination is now a sum of independent things. So this is the kind of proxy that we are going to end up getting. So just to summarize that this is a lot of notation, let me summarize that, plug this back into rephrasing our theorem. So the theorem now we want to prove is that for this psi estimator, we want to show that with high probability over the sample set X, overall any mean zero variance one distribution, it must be the case that for any pair of bad mean estimate candidate estimate and every single alpha, there must exist this d mu d alpha like parameter such that the linear combination is bigger than 0. So hopefully this at least smells somewhat like something that we can prove with the Chernoff bound at this point. So again, this linear combination smells like a sum of independent terms, except it isn't quite. This is not something we can still prove with the Chernoff bound. And the issue is in the quantifier structure of the statement here. So in particular, we have this following quantifier structure. We have a probability, and then we have quantifiers inside the probability, and then some inequality happening. And the Chernoff bound can only prove things without any quantification inside the probabilities, the scope of the probability. So the very natural thing, the final thing we're going to do is simply take these quantifiers and yank them out outside the outside the probability, which gives me finally this lemma, which says that consider any arbitrary mean zero variance one distribution, and then consider any pair of bad candidate estimates. It must be the case that there exists some constant such that over high probability over my sample set, I have this linear combination being bigger than 0. Now, this is something I can actually prove with the Chernoff bound. And I can turn this back into my main theorem via very standard like discretization and union bound techniques. And yeah, and I can now prove this with a Chernoff bound. I've got these linear combination that is a sum of independent terms. Does that kind of make sense? Okay, so what I've done, just to summarize what I've done, even if you didn't follow like the somewhat technical derivation I showed you, what I've done is find proxies of the estimator through these psi functions that is a, that are sums of independent terms, and then we can prove Chernoff bounds about them. And that will suffice to show, concentration guarantees about my estimator. What I now want to show you is how exactly do we prove these Chernoff bounds? Because that is still a very major technical question to resolve. And that I'm going to use mathematical programming techniques to do that. So let me put the excuse me. Let me put the lemma there again. So again, for arbitrary distribution, arbitrary bad pair of estimates, there exists some coefficient such that the dot product is bigger than 0. Let me just turn that into something like a tail bound and just flip the inequality such that the less than or equal 0 probability is small, less than or equal to delta. Now, what does it mean to actually prove this lemma? This is the question. I claim that proving this lemma is equivalent to bounding the following max-min optimization problem. Let me explain what this is doing. Okay, so the probability is the thing that is the objective. So that's the insight. And the probability is something we want to be small because it's a failure probability. Now, what about these two like max-min quantification? So recall that Okay, so we're going to quantify over these bad pairs of estimates. And then we're going to have a universal quantification. So worst case bound over all distributions. Now, because the thing we want to optimize, we want it to be small. If we want to take the worst case, then we better have a maximization here. And then because these d mu and d alpha parameters, we only need the existence of them. So again, because the probability we want to be small, all we have to do is take a minimization problem here. Does that make sense? The correspondence between this lemma and this max-min optimization problem. So worst case, we get to choose minimize the probability. Now, this program is complicated, I claim, because this is really an infinite dimensional problem. So the way to think about this is that there's a variable p sub x denoting the probability mass at each point x. So this is an uncountably infinite dimensional optimization problem if you ignore the formalization issues. So the question is, okay, so how do we actually bound this optimization problem? And I'm going to show you through a series of inequality on this slide to turn it into something that is nicer looking over this slide and next slide. Okay, so the first thing I'm going to do is to apply the Chernoff bound, as I promised before. So this failure probability is bounded by this moment generating function-like thing, this expectation of some exponential. And the next thing I'm going to do is I'm going to swap the order of the min and the max. And this is always true. This is always upper bounded by the other order by a standard, very standard min-max inequality. Now, doing this sort of stuff, there's always the lingering question: are we introducing a lot of slack in the bounding of the inequality? And the nice thing about this problem is that it doesn't. In fact, this inequality is going to be an equality because we can apply a minimax theorem to it. Like, it's possible to verify that this objective is convex in these d mu and d alpha, for example, because it appears in the exponent, and it's linear in these p sub x variables that I mentioned before. So this inequality is in fact a tight equality. And this is a duality in convex concave programming that allows me to just swap the max and the min. So having swapped that, the next thing I'm going to do is, so the other thing I was jumping up and down about is that the moment generating function, this is about a sum of independent terms. So I'm going to factor out the n samples and just factor out the exponent of n and give me this quantity here. And finally, the final observation is that this inner maximization is in fact a linear program that I'm going to show you on the next slide. Okay, so this maximization problem, I claim, is just this linear program. So as I mentioned before, there are a bunch of variables, p sub x denoting the probability mass at point x. And there are three constraints, very simple constraints. Well, we want it to be a probability distribution, so that it should have unit probability mass. We want mean 0 and variance 1, as I mentioned earlier as part of our simplifying assumptions, that we only analyze the estimator for mean 0 and variance 1 distributions. And lastly, I just want to point out that the objective is also linear in these p sub x variables because it's an expectation. Like, however complicated this inner function is that we're taking expectation of, it's always a linear function in these like p sub x variables denoting the distribution. So looking at this very simple linear program, what we're now able to do is to take the dual. Why do we want to take the dual? That's because instead of having infinitely many variables, we have three primal constraints, namely that we only have three dual variables. Okay, so what I'm going to do, well, sorry, what I have done is essentially turn an infinite dimensional optimization problem into a finite dimensional one with finitely many variables. Okay, so if I take the dual and plug it back in over my previous slide, I've now turned it into a min-min optimization problem with only 5 variables. It doesn't really matter exactly what the dual program looks like. The point here is that there's only a small finite number of variables. And this is a much more tractable thing to analyze. And in fact, at this point, there's a little bit more details, but essentially, because of the finite dimensionality, if you don't need to write down a proof, you can convince yourself of the truth of this lemma just by doing MATLAB and doing a grid search, essentially. So summarizing, what I've done here, I've started out with this somewhat horrible looking max-min optimization problem to bound the failure probability. I used a minimax theorem, a convex concave duality, and then I used linear programming duality to turn it into something finite dimensional. And going from this to this allows me to actually analyze this very horrible object to begin with. This is now finite dimensional with very few dimensions. So summarizing for the entire analysis, we started out with the main theorem. We found proxies of the estimator that are sums of independent terms, starting out with a sum of dependent things with a hard to analyze estimator. Looking at these proxies, we want to prove turn-off bounds about them, but that's difficult because it's like an infinite dimensional optimization problem. We use various dualities to turn it into something finite dimensional. And at that point, we can either MATLAB or actually write down inequalities to actually show that the objective of the optimization problem is bounded, thereby proving our turn-off bounds on these proxies and thereby proving the main theorem. So that wraps up the technical part of the talk. And again, summarizing what I've actually shown you, I've shown you an estimator with a really tight sample complexity that's not only big O tight, but even gets the constant right for all finite variance distributions. And that contrasts previous work that need far stronger assumptions or are only big O tight. I've shown you an estimator that is very simple. In fact, it fits on one slide and can very well be implemented by a beginning programmer. And I've also shown you, this kind of two-step framework of analyzing certain types of estimators that are sums of dependent variables of a certain kind of dependency structure. And I guess for future work, there's so many interesting questions that one could ask. From this point onwards, there's the high dimensional questions. As there were questions about that, like what's the situation in high dimensions? That's a much more complicated question that my advisor Paul and I we're working on right now. They also relate to computational questions. So the estimator I showed you, it's easy to implement in a RAM kind of model, but there are questions about can we actually do it in the streaming model? That doesn't seem obvious to me. What about various distributed models where, let's say, your samples are adversarially distributed in various ways? And yeah, with that, I'm ending the talk here, and I'm happy to take more questions.
Cool. Yeah, thanks a lot, Jasper. This was an excellent talk. Are there questions from anyone in the audience? So there was one question I had about like the statement of the results, I guess. This is sort of like maybe a subtlety, but I've heard about it a bit before, so maybe you can clarify. There's some about the delta being known. Like I know sometimes, yours requires delta to be given as an input parameter.
Yeah.
And I think it's impossible to get the same thing if you don't have delta as an input parameter. Like I thought there was a paper by Luc de Vroy et al. And this.
Yeah. So this that's what they call so our estimator they call a single delta estimator, and they were looking at this notion of multiple delta estimators that doesn't take delta as an input but holds for a wide range of delta values, and yeah, they show that that's impossible in general without additional more than finite variance assumptions. And in fact, I think the lower bound examples are just a family of Bernoulli distributions. So some asymptotic family of Bernoulli coins as they make the coin biases like rarer, yeah, to simulate heavy tailness, essentially, I think.
Sure, I guess that kind of makes sense in the sense that like you kind of need to know what sort of tail correction you have to deal with. You can't correct for all tails at once. It's very vague, but
yeah.
Okay.
So even okay. Now that you mention it, even on this slide, like the correction that I am showing you here intrinsically depends on delta, right? Like there's no single correction that applies to all delta because the delta tail, like the gap here is essentially exactly 1/3 log 1 over delta. So that's yeah. You need to know delta for this.
All right, are there any other questions? I have more things, but they get a little bit more, I guess, technical, so I won't make everyone sit through them.
Can I ask one?
Go for it.
Yeah.
Let me open my video. So I look at the estimator you have. My very high level understanding is you try to remove some samples from your data, right? By tuning this
fractionally. Yeah, fractionally, but yes.
Basically, you're removing 1/3 log 1 over data. Point. And then if you look at your estimator, you're normalizing, still using n as your in your denominator. Why didn't you just normalize by the sum of 1 minus alpha xi squared positive. Because you had
I see.
not the convex combination of the points that are survived, right?
Right. So you're asking basically that now we've kind of truncated a little bit of the mass out. Like, why aren't we normalizing by that weight?
Yeah, exactly.
I guess there are two answers to that. I'm not sure how satisfactory the answers would be. The first answer is that would be even more horrible to analyze. And we already had so much trouble analyzing this. I'm not sure I want to analyze that thing. The other thing is that, okay, one thing I was kind of punting on is exactly what the little or one means in our result. So the little one, so exactly what convergence regime we're considering. So there's nothing I'm lying to you about. So what we're doing is essentially the most general possible. So I didn't discuss it, but I'm not lying to you, I promise. But essentially what happens here is that we need, so for the little one attempt to go to 0, what we need is for delta to go to 0, and also the ratio of log 1 over delta divided by n to go to 0. So that's what our little one term means. So in that sense, because we're only throwing away a negligible fraction, so we have n samples, we're throwing away all the log 1 over delta much sample in there. So in this kind of asymptotic regime, it doesn't really change anything. And in particular, in this asymptotic regime, if you fix delta and then take this to 0, so not quite the asymptotic regime, sorry. So if you fix delta and then take the ratio to 0, our estimator approaches the sample mean in the limit sense. So yeah, I think what we're doing is reasonable here. That considering the asymptotic regime, that just dividing by n is, I think it's statistically is okay.
Right. Yeah, you're right. I completely agree that when n is big, it makes little difference. Okay. My other question is, it seems like to me you're doing a Z estimator, right? Because you're looking for the zeros of a nonlinear equation. Is it possible to show your estimator is actually an M estimator, minimizing some underlying, loss function, convex?
Yeah. We haven't thought about that. So we okay. Let me think through. Right. So currently, the way I phrase the estimator, there's the slide of this estimator is what our estimator is actually doing, which is not a Z or psi estimator at all. So this is what the estimator is actually doing. But for the purposes of analysis, we kind of rephrased a simplified version of the estimator. It's hard to scroll. So I rephrased a simplified version of the estimator as a Z estimator. Yeah. So one thing that is not actually a question, but I just want to make the point that it is possible to find a Z estimator version of our estimator. So there's a slightly different presentation. I phrase it that way because it's computationally efficient. But yeah, it is possible to phrase our result as a Z estimator as well.
Because
now
because then there is like standard concentration results for Z estimate or M estimate, right? I just wondering, like, is it possible to leverage on the existing results on Z estimator?
Oh, I see. I see. My hunch is no. I mean, we really haven't thought about that. So even in Catoni's work, so Catoni was focusing on the special case where you know exactly what the variance is. So in his case, answering your original question, he was writing down a psi or Z estimator, not an M estimator. And yeah, even he was punting on the fact that sure, it's not an M estimator, but it works. The other thing I want to mention, answering your second question, is that for one thing, we currently have a 2-parameter like Z estimator. I'm not familiar with many results on like a 2-parameter version. Like many of the results I've seen are a single psi equation with a single parameter you're trying to estimate. Here we have 2 things. which is kind of the reason why we need to go through all this trouble of, in order to prove a concentration bound.
Okay.
I hope that answered your question.
Yeah, thank you.
I have a question or two related to like Yao Liang's first question. I guess let me sort of ask them together. The first one is like, how nasty is this little O(1) term? You sort of made reference to like the fact that, as long as these things go to 0, then we're fine. But on the other hand, I'm curious, like, is it really a nasty, convergence in this little O term? Like, it would actually be significant for smaller values of n and like certain values of delta or not? And sort of a related question is like, okay, I'm going to steal something my student pointed out to me. Like, this is called, optimal mean estimation in R. Have you implemented this in R, like the programming language, or like any sort of implementation to see like whether this does this give like pretty much how good is this empirically?
Very reasonable questions. Yes. So let me answer the first question about the little O(1) term. So let me phrase it as a bad news, good news way. So the bad news is that the little O(1) term, or rather the 1 plus little O(1) term, if I recall correctly, is a product of two things. I'm just going to write out the expression. So there's one, slackness in little O(1) that is at the ratio of log 1 over delta divided by log delta, and then multiplied by 1 plus, I think, big O of square root of log 1 over delta divided by n. So these two things are appearing in like a product of two terms, essentially. Now, looking at this, you might very reasonably say that this log 1 over delta divided by log delta tends to 0 really slowly. And in fact, it gets small only when, let's say in a experimental physics kind of large hadron collider, smashing particles kind of regime. I think that this term is actually a little bit better. This term I'm not so worried about. Now, so that's the bad news. The good news, though, is how I phrase the theorem. The theorem says that our estimator taking n samples, taking delta, it's guaranteed to have convergence. It's just that we haven't tried optimizing the little O(1) term in analysis. The true performance of the estimator could be a lot better. So the fact that we weren't able to optimize the little O(1) term in the analysis doesn't mean that it necessarily have such a bad behavior. And in particular, the computation of the estimator does not depend on what kind of guarantees we were able to prove. You just run the estimator and it gives you, whatever the best performance it does have. So that's the good news part. Now, in terms of implementation, I'm afraid I don't have a good answer to that because I haven't had the time to actually try experimenting with the estimator. I've been trying to write the thesis and applying to postdocs and stuff. So that's definitely on my list. So that's the bad news part. But now back to the good news part. As I mentioned, as long as the ratio of log 1 over delta divided by n tends to 0, our estimator tends to the sample mean. So in the regime when delta is moderate, relative to n, that's the sort of regime where we recover at least the good performance of sample mean in practice. So at least there's a theoretical reason why our estimator does deserve to work in practice as well. But of course, I really should try to experiment on that.
I see. Okay, thanks. Yeah, are there any other questions that people want to ask now? We'll, I guess, stop the recording in a second. We can like take further questions offline, but if there's anything else that people want to chat about now.
And of course, you think of anything later, feel free to shoot me an email. I'd be more than happy to discuss.
Cool. But anyway, yeah, thanks again, Jasper, for giving the talk.